Dear students, this is our quantum mechanics lecture number 2. In our previous lecture, we were discussing about some key ideas of quantum mechanics. And in our lecture 1, we discussed about the linearity in the quantum mechanics, that how the quantum mechanics linear theory. Now we are going to discuss how the complex numbers are essential. That is, how complex numbers are necessary in the quantum mechanics. So, as you know that we can write Schrödinger wave equation. Schrödinger wave equation can be written like iota h squared partial psi over partial t and is equals to h psi. So here you have the term iota. Here this term is a complex number. Iota is a complex number. And this equals to iota is equals to minus 1 under root. So when people invented this quantum number, this complex number iota, so it's become very easy to solve equation like x squared is equals to minus 1. So with iota, now we can solve any polynomial equation. We don't need other numbers. So we can solve any number of polynomial equation with iota equal to minus 1 under root. So this one is the complex number. And iota square equals to minus 1. Now let's suppose we have the equation like z. We have a z equals to a plus iota b. So here a and b, these belongs to real number. These belongs to real number, and so the real part of z, real of z equals to a, and here the second part of this equation, the imaginary part of the z, and imaginary of z is equals to iota b. And we can also write the complex conjugate of the z as real one. If this z is equals to a plus iota b, and the conjugate of the z, this will be equals to a minus iota b. So we can also picture the complex numbers like this one, as this one is our, these are our axes, and so here a is on the x-axis real part and b on the y-axis, and so here z is equal to a plus iota b. We can write it like a is here and b1 is here, and so z will be equal to, that is the projection on a, and this one is the projection on y-axis, will be equal to imaginary part, and projection on the x-axis is equal to real part. So graphically we can represent the complex number like this one. So this is real part, this one is the real part, and this one is iota b is the imaginary part. Okay, so norm of complex number. You can also write the norm of complex number. This norm will be equals to, you can write the norm square, norm z square, and it will be equals to z multiplied by its conjugate, and it will be equals to a square plus b square under root, and this one is always real. So the norm square of complex number is the real. It is very important. This one is very important. And now here we have another identity which is very useful to discuss in the case of complex number. Let's suppose we have a complex plane, and here we have the complex plane, and this one is the circle with unit radius. And so here is our complex number z, and so making an angle theta, and this one is the radius, circle of radius 1, that is of unit radius. And so here the norm of z on x-axis will be equals to z is equal to cos of theta. And so as I have already told you that what on the x-axis represents the real part, and here projection on the y-axis will be equal to z will be equal to iota sine theta, that is imaginary part. So we can write the z will be equals to cos of theta plus iota sine of theta. So the complex numbers, we use them in the electromagnetism, you sometimes use them in the classical mechanics as well. So now we comes to the quantum mechanics, how we can use the quantum number in the complex number in quantum mechanics. Now in quantum mechanics we have the dynamical variable psi, and psi is the complex number. Here psi is the complex number. And since the complex numbers cannot be measured directly and we cannot measure them, so here is the, you can say that, indirect relation between the wave functions and the measurable quantity. So there must be, this is the kind of the indirect relation. And so there was a Max Born who interpreted the wave function as a norm here of the wave function. So amplitude here, and this square and name it as a norm, a square of the norm of wave function, which encodes the probability. So if we write the wave function for our system, and we can write it as a possible probabilities, and this will be equal to psi amplitude square, and this will always be, these are the probabilities, and you know that probabilities are always real. So this was the most accurate interpretation of the wave function by the Max Born. So psi must be a complex number. So it is complex number, and this norm amplitude square is equals to the probabilities, and probabilities are always real in the quantum mechanics. And the whole mathematical framework of the quantum mechanics, and whole mathematical framework required to express the law of quantum mechanics consists of complex vector space. So in quantum mechanics, you have the complex vector space. And this complex vector space have all wave functions. All wave functions. This wave function is also called as the state of the system. It is also called as the vectors. So this complex, this space which contains all the wave function is also called as complex vector space. So In the complex vector space, any vectors or in any vector space, we can have the object called the vectors that can be added together. In complex vector space, a vector can be multiplied by a complex number, also still a vector. So it is useful to think the psi as a vector in some complex vector space. So this tells us how the complex numbers are necessary in quantum mechanics, because the dynamical variable psi itself is a complex number, and whole quantum mechanics based on the interpretation of this complex number psi, which is also called as wave function, vector, and as well as the state. So these are the different names for the wave function, which is complex number. Thanks for watching. For more videos, please subscribe our channel.